Hey everyone. So for this session, we're going to talk briefly about the mass of the Milky Way galaxy as a whole and compare that to the masses of some other galaxies. Now, we've talked in earlier sessions how if I want to figure out the mass of an object, most of the time we have to use something about our understanding of gravity. The Newtonian gravity equation depends on the masses of the two objects. So if we want to determine the mass of some object, we want to look at objects that are in orbit around each other. So for example, if I want to figure out the mass of the sun, then I want to look at the orbital motions of planets going around the sun. If I want to measure the mass of, say, Jupiter, well, look at the moons orbiting around Jupiter. If I want to measure the mass of binary star systems, well, we need two stars in that system in order to get that kind of an orbit and determine its mass. And we also talked about that with the mass of the supermassive black hole that's at the center of our Milky Way galaxy, saying if there's this supermassive black hole at the center of our galaxy, let's look at all of the stars that are orbiting around that object, whatever it happens to be. Let's look at the motion of those stars, and by measuring their orbital properties, we can figure out how much mass is there. So we've talked about this a couple of times. Again, determine the mass of the sun from the orbits of the planets, determine the mass of Jupiter from the orbits of the moon. And basically, if I have one object orbiting another, if I can measure its orbital radius and either the velocity or the period of that orbit, we can use this modified version of Kepler's third law to determine how much mass is inside of that orbit. We're hopefully all still familiar with the Kepler's third law equation, p squared equals a cubed, where p is the period of the orbit measured in years, a is the semi-major axis of the orbit, basically the size of the orbit measured in astronomical units. And when we use that equation for looking at the motion of planets, asteroids, and comets inside of our own solar system, well, the dominant mass by far in our solar system is the mass of the sun. And in solar masses, that's just equal to 1. Let me reset my camera for a second. A little blurry, sorry about that. So when we're looking at this inside the solar system, our sun is the dominant mass, and this mass term would just be equal to 1. And we get that back, that p squared equals a cubed. But more generally, if we have other objects orbiting around each other, we can use this equation and say, well, this mass is just going to be whatever is inside of that orbit that we are observing. So we can rearrange this equation. So if we rearrange this to get the mass inside of some orbit is equal to the semi-major axis of that orbit cubed divided by the period of that orbit squared. Again, this is in, the mass is in solar masses, the period is measured in years, and the semi-major axis is measured in astronomical units. And this can be used basically anywhere. Again, the original version of Kepler's third law was only valid inside of our solar system. This one, we can apply that pretty much anywhere. So our sun, if we look at the motion of our sun, if we know, well, our sun is approximately 28,000 light years from the center of our galaxy. This is not actually the Milky Way galaxy. We can't get images like this of our own Milky Way galaxy because we are inside of the Milky Way galaxy. But just as a comparison, our sun is orbiting at a distance of around 28,000 light years, which is about 1.77 billion astronomical units. Based on how fast the sun is moving, relative to the center of the Milky Way galaxy, we can say with a high degree of accuracy that it takes around 230 million years for that object to make a full orbit, for our sun to fully orbit around the Milky Way galaxy. So if we take this equation and say, well, that semi-major axis is 1.77 billion astronomical units, and we cube that. And then we say the period of our sun's motion around the Milky Way galaxy is about 230 million years, and we have to square that in this equation. If we put in all of those calculations, we find that the amount of stuff inside of the orbit of our sun is approximately 100 billion solar masses. So inside orbit of sun in the Milky Way galaxy is approximately 100 billion solar masses. Now, we might not just want to know, well, how much mass is inside of the orbit of our sun. We might want to know, well, how is that mass distributed? Is it all right near the center? Is it evenly spread out? Is it clumped in different kinds of ways? Well, to find out how this mass is distributed, what we can do is look at the orbits of other objects, objects that are closer to the center of the Milky Way galaxy, and further out in the Milky Way galaxy. And if I can identify how much mass is in one of these smaller orbits, and then mass inside a medium orbit, then mass inside a larger and larger orbits, if we can get all those different masses, we can figure out how the mass is distributed inside of the Milky Way galaxy. So let's look at some possibilities on what these kind of mass distributions might look like. When we use our solar system as a comparison point, we know that the vast majority of the mass of the solar system is just the sun. So basically, all of the mass of our solar system is right at the center of our solar system. Our sun is 99.8% of the mass of the solar system. So if this mass is staying the same, as that semi-major axis increases, the period is also going to increase in such a way that orbital speeds drop pretty dramatically as you get further and further away from the sun. Any system where most of the mass is really, really centralized will have this kind of a graph of orbital speed versus mean distance from the sun. So as you go further away, further out in this kind of a system where all that mass is centrally located, the orbital speeds will drop off dramatically. Well, we can do a survey of the Milky Way galaxy. We can look at all the stars that are out there. We can look at their general sizes. Again, we have ways of measuring the masses of stars, so we can kind of predict how much mass there is. We can also look at all of the clouds of dust and gas. Remember, our Milky Way galaxy, especially in the disk of the Milky Way galaxy, has a lot of dust and gas, probably more mass in dust and gas than there is in all the different stars. But we can also get estimates of the masses of those clouds. And based on this, we could make a prediction for if our understanding of these masses, the masses of stars, the masses of gas and dust clouds, if our understanding of the masses of these objects is correct, and this is all that's out there, we can make a prediction on how the orbital speeds outside should change. If I know the mass and I know where these objects are located, some orbiting objects are located, I should be able to predict how fast are they moving, what are the periods of those motions. So when we do this, the dashed line, case A, that is the expected speeds based on how much visible matter we see in the galaxy. Things like stars, clouds of dust and gas, based on all those things that we have seen and have kind of talked about a little bit already in the course, we can get estimates of how fast things should be orbiting around the Milky Way galaxy based on those objects. What we actually get is something that looks more like case B, that the orbital speeds stay much, much higher than we would expect based on just the visible matter that we see in our galaxy. This is a little bit more of a detailed case where this is looking at orbital speeds, again, in the Milky Way galaxy versus distance from the center of the galaxy. And what we predict is this solid line that the orbital velocities should gradually decrease as you get further and further away from the center of the Milky Way galaxy. All these circles are what we actually observe. So you might ask yourself, how do the predictions, the predicted speeds, compare with the actual speeds? And in this case, they really don't match up. There is something that we are missing here. Our predicted values did not match the actual observations that were taken. So what we actually observe is, instead of the speeds dropping off quite dramatically as you get further and further away from the galactic center, those speeds stay very high. Maybe our galaxy is just a fluke, but when we look at other galaxies and do the same kind of measurement, saying these are the stars that we see, these are the gas and dust clouds that we see, these are their estimated masses, we can predict what the orbital speeds of all of these objects should be at different points in this galaxy. But what we actually observe is, again, very different when we look at basically all different kinds of galaxies. So instead of the velocities dropping off, instead of these orbital velocities, getting slower and slower as you go further away, the orbital velocities stay pretty quick. Well, what could account for this? We are seeing at these greater distances, we still have fairly short orbital periods. So the orbital periods and the orbital period is faster than what we'd expect just from the mass alone. So, sorry, that orbital period should be decreased if we're saying it's faster than we would, it's moving faster than we would otherwise expect. Which means if I'm going to greater distances and the period is lower than I expect, this mass inside of those orbits must be much greater than we were expecting. Basically, there's more gravitational force, and it's pulling these stars and gas and dust clouds in the outer parts of these galaxies. It's pulling those into faster and faster orbits with shorter and shorter periods. So the solution seems to be there's more mass present than can be accounted for by just the stars, the gas and dust clouds, by all of those things that we can see. So when we talked about our Milky Way galaxy, we said we've got the galactic center, the bulge in the middle. We've got this disk of material where there's lots of gas and dust. And we have this halo that is mostly empty except for these globular clusters. So we get this halo of luminous matter, but the evidence right now suggests that there's a much larger and much more massive halo of non-luminous material. So let me kind of summarize a couple of those important points. There seems to be more mass present. Than we can see. Based on higher orbital speeds far out in these galaxies. So that's based on higher than expected orbital speeds. So one of the potential solutions to this is maybe there is some extra matter out there that we cannot see as of yet, that we cannot directly detect. This material, this mass that we can't directly detect yet, we can only indirectly detect it based on how it gravitationally affects the rest of the galaxy around it. We have this material that we call dark matter. So there might be a large quantity of space for this, of non-luminous dark matter. Again, at this current point, and again, hopefully this video doesn't get dated or anything if we have some, new detections, we are not yet sure on what this dark matter is. Later on in the course, we'll talk about what are some possible candidates for dark matter, what is some of the new research going on in dark matter, what are kind of some of our ideas about dark matter. Right now, that is just a placeholder name for whatever this material is that's gravitationally influencing the material around it and causing the motions of these objects in these galaxies to move much faster. So again, although we can detect dark matter's gravitational effects on the motion of galaxies and clusters of galaxies, we do not know what this dark matter is. Dark matter is just a placeholder name for there's something affecting these galaxies. And this dark matter, this discrepancy between we expect this much matter, we observe based on the orbital speeds of these galaxies, we observe that there should be this much matter. It's not even really close. This halo of dark matter surrounding the Milky Way Galaxy probably extends somewhere around 10 times beyond the visible galaxy itself. So if this is the visible galaxy, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about this much further away, a giant halo around that. It could contain between 15 to 20 times more mass than the entire visible galaxy. The majority of our galaxy might be this unknown dark matter. And this dark matter, while it interacts gravitationally with normal matter, it does not interact with light in any way. It doesn't emit light, it doesn't reflect light, it doesn't even block light. When we were looking at those pictures of gas and dust clouds in space, we'll be seeing more as we talk more about some of the properties of galaxies. Some of those gas and dust clouds, even though they don't give off a lot of their own light, if they block some background stars, it'll look like this kind of big dark area in space because it's blocking the light from those background stars. This dark matter material does not even block light. It can't get in the way of ordinary light. Light would just pass through this dark matter without being affected. So again, there's a lot of open questions as to what this dark matter is. But even though we don't know what this dark matter is, the mass associated with this dark matter seems to make up between 90 and 95% of the mass of the Milky Way. So again, it's a huge influence on the structure of our Milky Way galaxy. It's a huge player in how our galaxy operates, but we know very little about it. We'll talk more about it later on in the course, but the main things for this session is just saying, well, how do we actually measure the mass of the galaxy? How do we measure how that mass is distributed? By looking at how much mass is inside this part of the orbit, how much mass is in this side part of the orbit, and so on and so forth. And again, the overall points are there seems to be much more mass present than we account for by the objects that are luminous that we can see, stars, gas and dust clouds, things like that. So again, later on in the course, we'll talk about what this dark matter actually might be.